All right, well, welcome again to the YouTube classroom, and I have another paper here that I want to talk about. This is going to be a video on inefficient face detection in schizophrenia, which is a paper by Chen et al. In 2008, and this was actually the first paper really that I was on in my research career, the first paper that I was included as an author on. That was really collecting its own data and stuff. I was on one review article before this, but this was my first real scientific paper in a way. So it's has a special place in my heart. I think I'll talk about a few things in the paper. You can read the paper, you can see it. I think you can understand it yourself. It's nothing too crazy is in here, but I'll hopefully be able to enrich your understanding of it a little bit and help you to kind of speed up the process of absorbing it by walking you through a few things here. So basically this is one of a few papers I assigned in the class on social aspects of social cognition in schizophrenia. So social cognition meaning thinking that has to do with social interactions, and face perception is one aspect of social cognition. Perceiving someone else's face, knowing who they are, what expression they have on, whether they're male or female, whether they're friend or foe. These are all aspects of our vision that are really important for us to do well socially. Another aspect, I think, in some of the papers I assigned is called biological motion perception, which is where you have basically little white balls on people's joints, and you video them moving around, and then you edit the video so that all you see is the white balls, and you can kind of tell what the person is doing. So perceiving just from dots moving around, perceiving someone's motion, that's what biological motion is. And there's another paper on Blackboard about by Kim et al. About that and how that's deficient in schizophrenia. I'll leave you to judge whether it's a real specific deficit or if it's really just a generalized deficit, and it's like in the Chapman and Chapman video, I discussed some of those issues of distinguishing real specific deficits versus generalized deficits that just don't have a very good control task. So that issue comes into play too with this paper by Chen. So basically this is a study on the face perception part of social cognition and how that might be messed up in schizophrenia. People with schizophrenia, I think I might have mentioned this in class, but actually the word autism was originally coined as a symptom of schizophrenia. It wasn't its own disorder. It was referring to people with schizophrenia who are autistic, meaning they kind of socially withdraw, or they have social problems, they don't connect with people well. And this is something, it's one of the negative symptoms of schizophrenia, is social withdrawal and not having normal social relationships. And people wonder, is one reason for that maybe because their social cognition is off? They're parts of their brain that are involved in seeing other people and seeing social cues and stuff. Are they messed up? And that's part of the reason for social problems in schizophrenia. So that's sort of the underlying impetus behind papers like this. There's a lot of papers that have been done like this. This was way back in 2008. I think Chen had a good intuition that faces were getting to be a hot thing to study. Now they're the most commonly used stimulus in all of psychology, is faces. And he was sort of on the forefront of that, I'd say, in the mid-2000s doing this paper. So this paper is on inefficient face detection. So a lot of people have measured emotion recognition in schizophrenia and in other disorders. So can you recognize, what emotion is on my face? You probably could recognize those three if I did a good job expressing them. Usually people can, and you can make up tests to see how well people can do that. That's a very popular thing to do. People do it in a lot of different disorders. Face detection is a less popular thing to study, but I think it's a really cool thing to study, a really important thing to study. And basically the idea here, and this is spelled out really well in the introduction. If you want to read a pretty good introduction, I think this paper has one. And you can try to borrow some of the ideas about how Chen explains his study from this intro, from when you're writing your intro to your research report if you're in the lab. Or even when you're trying to explain your specific aims, some of these ideas, ways to explain might be useful. So let's actually just run through some of the intro together real quick here. So it starts off by saying, while recognizing a face appears to be really easy for us to do. It's important socially, and if it's messed up, it could impact you socially. That's basically what the first paragraph says. And then it goes on to say what I said, that there's a lot of different aspects to face recognition. There's recognizing the emotion, there's recognizing who it is, recognizing how old the person is, and these different aspects of face recognition are done by very specialized machinery in our brains. You guys remember the fusiform face area I've talked about already is an area right about here that is specialized for processing these things about faces. But in order to use your fusiform face area, you have to know that you're looking at a face. There has to be a part of your brain that detects a face in the visual field and then unleashes all this specialized machinery to analyze, who it is and what emotion is on. So face detection is a really important part. It's the first part of our brain's specialized face recognition hardware. But it's understudied. We don't really know whether people, for example, with schizophrenia who have messed up emotion recognition, is their face detection messed up to begin with. And maybe the noisy signals from face detection are going downstream and hampering the other aspects of face recognition, like emotion recognition. So that's more or less what it says in the intro. And then it says, they use these special stimuli and stuff. So this is basically what the study did. I will explain the stimuli now. So there were these line-drawn faces that were used. And they look like this. I'll make a picture of them come up here. But they're faces that are very simple. They don't have a race, really, that you can identify. They don't have a gender that you can identify. It's just a very simple face. And it was created in Photoshop from taking a photograph of someone's face and then filtering it out, making every pixel either black or white, and filtering out all the extraneous stuff like hair or other weird shadows that had to do with the lighting in the room or whatever, so that you can just see the most basic parts of the face, like the shadow of the eye, under the nose, the mouth, and you can tell it's a face from those very basic contrast signals of black against white. And then the task is just to say where the real face is. And the nice thing about this stimulus is that the non-face stuff that you're kind of finding the face within is all made of the same exact face shadows that the real face is made out of. The difference is that they're scrambled in the rest of the image, and in the real face that you're supposed to identify, you're supposed to say whether it's on the right or the left. There, it's in the right configuration. That's the only part where there's a face in its correct configuration. The rest is all scrambled. So it's a pretty cool stimulus. It's not like you can do the task. Like if it was face detection, if you want to do a face detection task, you might say, well, why don't you just show someone a picture where there's a face in the room, and they say, there's the face. Because we want to know, because there's these other low-level mechanisms you could use to do a task like that, where you'd be like, okay, I'm just going to look for the part that looks like skin colored. And if I find anything that looks like it could be skin, okay, that's where the face is. If it's one person in a room like I am right now, there's nothing else that's really skin colored in your view on the screen right now, so you can probably find my face by just looking for skin. And we didn't want that to be the case. We wanted it to be, you're really perceiving a face based on the configuration of eyes and nose and mouth and stuff. So that's what we did, and that was the task of interest. How well can you identify a face? We presented the face very quickly, somewhere between 13 and 100 milliseconds. So just a quick flash, really, and then you say, okay, in the thing you just saw, the quick flash, where was the face? Was it on the right or the left? And we also did the same thing with a tree. Scrambled a tree and had a tree in the correct configuration and said, find the tree. So that was our control task. Remember from the Chapman and Chapman mini lecture, we wanted to try to have our control task be as similar as possible to our real task of interest, which was face detection, and hopefully it would be matched on accuracy. But as you'll see in the results, they were not matched in accuracy. The face detection task, let's deal with that first, was pretty good, I would say, for accuracy. It was low 90s for the control group, 80s for the patient group. So there's a difference there in detecting faces. but not for inverted faces. So I forgot to mention this to this point. That was another condition we had, is we had upright faces and inverted faces. And it's been shown many times in the literature something called the face inversion effect, which is that if you take a face and you turn it upside down, it's much harder to A, tell that it's a face, and B, like tell things about it, like what emotion it has on and stuff. So we measured both upright and inverted faces because we wanted to see how big the face inversion effect would be in schizophrenia. People think that the reason the face inversion effect is there is because our brains are specialized for processing upright faces. And when you show someone a face that's upside down, your brain has to use more general hardware that it uses for looking at other stuff to analyze the face. It can't use its specialized face equipment if the face is upside down. And that's why people do worse on recognizing anything about a face if the face is upside down. So we thought that the extent to which the face inversion effect happened in schizophrenia would be, you have the overall accuracy score that people have on upright faces is one measure of whether they have messed up face detection, but another is how big is their face inversion effect. So that's why there's all these different lines here in this figure 2A. It's for upright and inverted faces for patients and controls. And then we had the same thing for tree detection, upright and inverted trees for patients and controls, and you can see that the accuracy is way up high for tree detection for all the groups, and it's much more spread out for face detection. So what we see here is that there's less of a face inversion effect for patients if you look at figure 2B. And figure 3B, there's no inversion effect for trees in either group, really. It's less than, it's the ratio of accuracy in upright versus inverted. And if it's 1, that would mean they have the same accuracy. So you can see for tree, for figure 3B, it's there's really no inversion effect for trees. But there is one for faces. It's smaller for patients. So that was sort of the take-home message of the paper, is that's why it's called inefficient face detection. What Chen meant by that was that there's less of a face inversion effect in patients than controls, which is cool. And I think he did a good job kind of making it a pretty good argument for that. But I was really never convinced by that argument, to be honest with you, because even though it was pretty good, and it got into Schizophrenia Bulletin, which is the best journal on schizophrenia specifically. It's a very, very high impact psychiatry journal. And it got into that journal, meaning he made a good argument, but I was never convinced because I think the data were affected by floor and or ceiling effects. So if you look here, the patients and controls for the inverted faces are very similar to each other in their accuracy. And that's partly, I think, because the data are starting to get clustered down by a floor. It's probably not happening for upright faces. Really, the reason that you get this difference here for the inversion effect is really a function of the upright faces and the fact that the inverted faces are the same. So if you take, numbers that are different and divide them by numbers that are the same, you're going to get numbers that are different, which is what's shown here. And here, the reason there's no difference on tree detection, remember this is our control task, why might that be? Think about Chapman and Chapman. It's because of a ceiling effect. Everyone's accuracy is getting clustered up to 100, and there's not much room to be different from each other if everyone's performing near perfection. So that's one of the drawbacks of this study. I think it was hard to anticipate because Chen did the right thing. He made these tasks. He collected pilot data on a few people, like his research assistants and maybe like a few naive controls, naive meaning they didn't know what the study was about. And the tasks looked good. They looked like they were similar in difficulty to each other. But it turned out when we collected the big sample that they weren't. And the tree detection task was basically too easy. And there was a ceiling effect there that made it so that we couldn't really make it. Our argument that there was a specific deficit in face detection that was not there in tree detection, I think was pretty weak because the tree detection task wasn't good enough. It wasn't a moderate difficulty level like it should have been. And if you're confused by that and you haven't watched the Chapman and Chapman video yet, go back and watch that, and that should make sense. All right, so that's sort of the take-home message from this study that I wanted to get out. There's other things that are mentioned, but that'll be good for now.